Hi, everyone. I'm not usually one to talk about myself. I was just going to jump into the material, but someone asked me, so I'll give you a small brief. I'm a full-time employee here at Stony University for about 23 years. I have a bachelor's and master's in computer and systems engineering. I currently work for the Department of Biomedical Informatics, working with medical imaging. And for fun, I'm a part-time PhD student here at Computer Science. I'm also the W3C Advisory Council rep for Stony Brook, so I get to go to all sorts of cool meetings and meet with cool people. So anyway, tonight's presentation is going to be very informal. There are 0 slides. There is source code, though. All the source code is available on GitHub via a link off the Stony Brook Semantic Web meetup site. But Paul asked me to do something simple, but this was actually a thought I had to do, because a lot of the presentations we've been doing for Stony Brook Semantic Web meetup have been sort of formal with slides and everything. So I thought it'd be interesting to just do something that's a little more hands-on to show people one way that they can actually get RDF linked data. How many people in the room are familiar with RDF? And how many people have no idea what the acronym means? It's fine, please be honest. Okay, very briefly. And correct me if I get any of the history wrong. But for me, this concept of the semantic web, at least the W3C's version of it, started somewhere circa 2000, 2001. There was a particular paper that came out that was authored by Tim Berners-Lee, James Hendler, and Laszlo, I think. And it talked about creating a web of data. It's a very simple concept that all of your data elements are represented in very simple statements. The subject, the thing you want to talk about, the predicate, the property or relationship for that subject, and then finally the value of that property or the other thing you're trying to relate it to. And in its use of URIs or ERIs, which are the cooler, more international versions of ERIs, your subject is always an ERI, your predicate is always an ERI, and your object can be an ERI or just a value or a literal, which would be sort of a leaf on a tree. And essentially, the subjects and the objects potentially link with each other, and they basically form a giant directed graph. And data can be found all over the web. One of the ways I'm going to show you tonight is one way that some of this RDF data is being available, and it's basically via a mechanism called content negotiation. Now, most people, when they're used to browsers, they go into their browser and they type a URI. And in most people's minds, a URI or URL equals a web page. But it's actually potentially multiple representations are available for that. Most systems are rigged only to do the HTML pages, or they're sort of hard-coded to be like a JPEG image or something of that nature. But you can set up your web servers such that you can actually request that server to give you a particular data type. Now, browsers are coded behind the scenes to do HTML, JPEG, a lot of the things that they're capable of displaying. And they're set in a certain order, and the server will dole it out depending on, I guess, whatever its mood is. But you can specifically request a particular data type. And one of the ways I would like to show you how to do that without even getting into the coding is essentially via an app that you can download in Chrome. I just need to turn this on. Here we go. So there's an app here that basically gives you a simple sort of RESTful client. It's sort of like a web browser without any of the graphics and without any of the features, but it does give you access to specify certain things that are happening behind the scenes without you realizing it. So in this particular case, let's just take it from the beginning. This is about a website called Crossref. Crossref is a search engine for basically going through a lot of publication data and such, and it ends up giving you a URI that basically will take you to article level information. So I'm going to do a search for something called MyGenes, which is a mitochondrial database that was done years ago. And so at the top of the page, I can see a link here, but it's actually for a person named MyGenes. It's not the one that I want. Let's see if I can find it. Not showing. Doesn't matter. So anyway, if I click on this link, say for this one, it actually redirects me to the website where that publication actually exists, in this case on Springer, and I can go directly to the article. And this is useful. I can now download my PDF and such. But Crossref for some time now has actually supported content negotiation. In order to do that, I can take that link and we're going to punch that into this client. And this particular client you can find on the App Store of Google Chrome. And we're going to take out this header for now. So now here I can specify one of the 4 major verbs for the web. A get, which is what you usually do when you type in a URL for a web page. Post, usually when you're filling out forms data, you'll send a post command. And then put and delete are used for other things that most people aren't aware of. So I'm just going to say a get as if I'm a browser. And what this is going to return back to me is essentially nothing in this case. But if I specify now the header known as accept, and I'm going to ask for basically text turtle, which is the official MIME type for Rdf Turtle. Let me show you how to get to this. It's a raw REST client. It allows you to sort of do some low-level HTTP work. There are a lot of programs that will do this. There's a program called curl. So curl at the command line, you can specify a couple options in URL, and it will do an HTTP request. Either pull down a web page, or you can use it to pull down files, zip files, tar files, all sorts of things. You could also use it in this case. But I like using this one because it's got the graphical interface on it, which makes it a little easier when you don't remember things off the top of your head. So let me go take a step back. And if I go to the web store here in Chrome, and I'm going to type REST. And there it is, the Advanced REST Client, which is something I'd found years ago, and I'd used it. It's already installed, so I don't have to install it, but usually you'll just say add Chrome, and it will download it into the browser, and usually you just got to restart the browser, and then it becomes available as one of the built-in apps that you can use. Yark is another one. There's several that will basically do the same thing, but this is the first one that, and I liked the way it had responded, so I had used it. Okay, so now with that URI and setting the accept header to text turtle, I'm basically going to do an HTTP get to that server again, but rather than asking for a web page, I want it to give me RDF data. Now, that concept that I told you about the subject, predicate, object, also known as a triple, RDF being a graph model is probably the most important aspect of RDF. But people get lost in the other aspect of RDF, and that RDF has multiple serializations for it. There's an RDF that's written in XML. There's an RDF that's written, it's fairly new, JSON. So it's the JSON representation. It's called JSON LD. It is JSON, just the way RDF XML is XML. There's RDFA, which is embedded RDF in web pages. There's also what's known as N-triple, which is sort of a very primitive version, but it's very easy to parse, where you actually specify the subject as a full URI, the predicate as a full URI, and then finally your object value or object URI. The representation I'm choosing, because it's a lot easier to read, is what's called Rdf Turtle. It's a complete superset of N-triple. So any N-triple will actually parse in by a Turtle reader. But Turtle introduces namespaces to simplify the syntax. It also introduces a few other shorthands. So you can see at the bottom of the page, I can now basically get, this is all that data that I would have gotten via the web page. I now have it as actual data. So in this first case, I have a subject here, and in Turtle, the notation allows you to specify multiple predicate objects after a particular subject. So the first thing that I'm talking about is represented by this URI here, and I can find out that it's of type person. A is an accepted notational shorthand in Turtle that basically stands for Rdf Type. So basically this is a type of person. Then I can see that they have a family name of, what is this, Potash. a given name of Joel, and then finally a sort of a full name specified as Joel Politosh. And I can follow that down, looking through and getting other data about the paper, including the pagination, the journal, and the very useful document object identifier, DOIs. So DOIs don't have anything to do with RDF. It is a, for those of you who don't know, it's a unique identifier for various publication data. And the DOI group sort of made a URI version of it so that it would work well with dereferenceable data. So cross-ref in conjunction with DOI, using this content negotiation, I can basically get everything downloaded that. But the article level web page is actually still good, and that's in the data. So if I wanted to, I could save all this, stick it into a file, and then do whatever I want with it. What I'd like to show next is now sort of a programmable way of doing it. So basically starting a web client inside of a Java program, and then taking that text RDF serialization that's downloaded and actually loaded into something where I can actually execute queries against it. For the people sort of new to RDF, there's a whole stack of technologies that come with. RDF is your sort of your substrate, how you actually represent the data. The next layer above that is going to be Sparkle, which is a query language. It has a very SQL-like appearance, if you're at least familiar with relational databases, but it's geared towards graphs. An important aspect of Sparkle to realize is that and you'll see some examples, but the where clause, the sort of the filter clause, is actually written in Rdf Turtle. So knowing Turtle for the data format, it also helps when you're actually writing Sparkle queries. All right, so if anyone wants to follow along, load up NetBeans, but the first thing that we're going to need is our web client, which is a Java library by the Eclipse Foundation called Jetty. It actually found Jetty years ago because, primarily because they also have a web server. So in a few lines of code, I could actually embed a web server inside my applications, but I found out later that it actually had a really nice client implementation. So just go to Downloads, and just download one of the newest versions here, the 9.3 version will do. And then you'll basically download the zip file to a folder. We'll call it, put an SBU folder for now. It's going slow. Well, like a good baking show, you actually have the cake done already. So I'll just go into my folder where I keep. So if I unzip that folder, I'll get a folder like Jetty distribution here, and here's all the different libraries. And I'm just going to show you this for now, and then sort of show you where to get the other libraries that we'll need, which is Apache Jenna. Jenna was actually started, I believe, by HP years ago, and it's now been brought in as a Tier 1 application with the Apache Foundation. So we want to download is the core here. These are the Jenna 3-point libraries. So if you download it on Windows, download the zip file. And eventually that'll download and you can unzip it. But I'm going to show you, I'm just going to jump and show you the unzipped version so we don't spend too much time. For the presentation, I'm going to use Jenna 3.01, but there's really no major changes, just bug fixes, some additional features, but it won't change the code. And those are my folders for Apache Jenna. So now to configure these inside of NetBeans. So NetBeans is something I think was started at Sun Microsystems. It's an open source Java integrated development environment. Eclipse is probably the next major competitor to them. I'd started using Eclipse. I thought it was really good and everything, but for me, my personal taste is Eclipse felt like it was designed by a lot of smart people, but for me, NetBeans feels like it was designed by one smart person. It felt less committee-ish. Eclipse is probably, I'm not trying to knock it, but Eclipse is very powerful, but I've always sort of been more of a NetBeans fan. So I can go into, once I have NetBeans loaded, I basically go into Tools, Libraries. Let's stretch this out. And I create a new library. I'm going to call the first one Jenna. I already have it configured, but I'm just going to do it here. So the first thing I'm going to want to do is add the actual binaries for the code. So now I'll have to go find them on my drive. And I basically want to add everything in the lib folder. Next, I want documentation, because I'll forget sometimes what a method does. And their particular distribution, they've got 3 folders. You just add the 3 in there. Oops, sorry. And if I want the sources, they're nice enough to include, I think, the sources for everything. So I just add the 3 sources here. And now Jenna's all ready to work with NetBeans. Now it's similar for Jetty, a little difference. I'm going to go into lib. And I'm going to add all these. There's some extra things like WebSocket support, but I find adding these adds what I need for most cases. Now the Java stuff is handled a little differently. If they have got a local version of it, I haven't figured it out yet. But back on that download page, this API docs link takes you to the Java docs. So if I take that and I come back over, I can now add a URL. And now that'll give me the documentation. I haven't really done too much with the sources for Jetty, so I'm not going to set that up. So now for my project, in order to make those libraries available, let me create a new project so I'll show you how it's set up. I pick a Java application. I'll give it a name, SBU. And now if I go into the properties of the project itself, and go into libraries, I then can add the libraries that I need. So I'm going to add the ones that I created here. So SBU Jetty, I think it was. And then add in Jenna. So now if I start writing the code, those libraries are available and they'll end up showing up. But I've already written the code. I'm not going to try to do it from off the top of my head. And I'm going to walk you through the code and show you what each piece does. I apologize to any non-programmers in the room because this is going to get a little bit. So I created a method called getRDF, which the idea is to pass it a string URL that I want to basically dereference and basically download Rdf Turtle, and I want it to return back what's called a Jenna model. A Jenna model is Jenna's object for holding a RDF graph, basically a blob of triples. It also gives you various methods to do some simple searching of it. They have a more sophisticated library called Arc, Jenna Arc. Jenna Arc allows you to actually run Sparkle queries against that memory-based RDF triple store, basically. So the first thing I want to do is set up my client. So define an HTTP client here, and this is a Jetty HTTP client. And I need this. A lot of the examples that show you how to use this will set follow redirects to false. It won't. The RDF redirection won't work. So you have to set it to true. And then finally, I start the client. So with these 3 lines, I've now started up a client to do this. The next part here is I'm going to set up my call here. It basically uses a content response. And these are just basically all chained off the same object. So I'm going to do HTTP client new request with the URL that was specified in the method call. I'm going to set my method to get, very similar to the way we did it in the REST client. Not entirely necessary, but some systems get a little weird when they don't recognize the browser coming in. So I'm basically mimicking a sort of Netscape-like browser with this string, but it's not necessary. The important part is now I'm setting the accept parameter to text turtle, and this is what's going to get me my RDF data downloaded. And then finally, I'm going to send the request. So by this point, after these many lines of code, the response basically contains the RDF data. And so if I say response get content as string, that will download, will not download, but it will display the RDF that was loaded. So let me see if I can get this to actually work live. So the output. The output worked. So it ran that thing where it said it was grabbing the particular URL that I wanted as turtle, and it then printed the value of the response back. So if we do a comparison with the other web page, we'll find out that this is the exact same RDF turtle as text that we had saw on the other page. But it's not quite useful yet. I want to be able to, as per the original specs of the presentation, I want to be able to load that data and actually do Sparkle queries against it, and I actually want to load it into what's called TDB. The Jenna model basically gives you a triple store in memory, but most people don't have enough memory to do things, so you want to use the hard drive for your space. So you want to basically do a disk-based type triple store. TDB is Jenna's triple store, or actually a quad store, because although I said there was triples, quite a few years ago they added a 4th parameter called a named graph, another URI. And the named graph, you could simply think of it as a grouper. You basically put a wrapper around a blob of triples. And so the next line in this method was, after we've displayed it, I basically grab all that text and I throw it into a string variable called TTL. At this point, I'm going to stop my HTTP client. The reason why I'm doing that is, I discovered this the hard way, Jetty's client gets spun off into a separate web, and if you don't explicitly stop it, it will basically, the program will look like it's still running. So I'm explicitly stopping it so the program terminates after I run it. I then basically wrap the TTL string, and I'm basically going to turn it into a stream that can be read into by Jetty. So to define a Jetty memory model, a Jenna memory model, I simply say model M, and then I use the model factory to basically create a default model. Basically, it's going to be an empty blank triple star with no triples in it. I then use the read method, and I'm going to pull from the IS, the input string, which I created out of that TTL by wrapping it in a Java byte array input stream. That's just a standard Java library. And I'm going to read it, and I'm telling it that it's turtle. Jenna will try to figure out what the format is, but it's helpful to hint because occasionally we'll get confused. So I explicitly tell it it's turtle. It will then read those triples into that memory store, and then finally it's going to print the number of triples downloaded will be m.size, and just print that out to the console. And I'm going to stop it here. Let's see if this works. So right there. So it said read downloaded TTL into Jenna model. Number of triples is 43 triples. That's represented by that dereferenced web page using content negotiation. There are no other methods in the sample code, but now I'm going to show you what's being run at the beginning. So the program actually begins here. That's just the definition that I walked you through for how it gets the RDF data from the website using content negotiation. But I now create a Jena model called M, which is different from the other one because that's one's wrapped inside that library, so it doesn't actually conflict. And by creating a object version of this program, I can now say RDF get this first URI, which contains dereferenced data off of Crossref. But then for grins and giggles, there's actually another website called WorldCat, which contains holdings information for libraries all over the world. And they're a big fan of linked to data. So I can actually basically use content negotiation to get data. This particular URI is actually for, let's see what I forgot. It should be Harry Potter. So I just type into the browser. Stony Brook actually has their own version of it, but I'm going to use the standard vanilla version. So there's Harry Potter and the Prisoner of Azkaban. But I'm going to submit it for content negotiation. I'm going to put that into another Jena model called N, and I'm going to basically combine the two into one big blob of triples. Okay. So let me just take it to here. Okay. Oh, I'm going to turn this off. Turn that off. Okay. So that ran through. Okay. All right, so that's all done. The next part we're going to do is after we've read the data in. Oops, sorry, I had one more stop in there. Take that out. Next part is where I want to show where we're going to do the first actual Sparkle query. So I've got these two blobs of triples loaded into a variable called M. So the first thing is we're going to construct my Sparkle string. So I'm going to do a Sparkle select, which is similar to a relational database select, but geared towards graphs. So I'm going to basically select the entire triple, in this case SPO. The variable names don't really matter. The position is what matters. The first position is always the subject. The second position in a triple is always the predicate, and the last is always the object. If I wanted to, I could change this to dirt, and dirt just became the predicate. Usually you'll pick an identifier that's a little more meaningful for the particular type of data you're looking for, but in this case, I'm looking for all the predicates. So I'm just going to call it P. I then feed this string into a Jena query factory, and then finally execute it, and it's going to pass the results back after I execute the select back into this variable called results. And then with this block, I can basically iterate through all the solutions for that. And in this case, it should come back and just sort of dump each of the triples back to the screen. So I'm going to pass it here. And let's see if that works. So there you can see each of the triples. And it just displayed it, and wasn't a very sort of sophisticated output, but it basically dumps them out, well, predicate object subjects for whatever reason. But these all map to the triples that are in that string representation, the turtle representation, but it's now in this object that I can do, well, just did a query against it.
Do you have queries that relate triples from the first repository to the triples in the second?
Directly off of those repositories, or once they're loaded in memory that I can relate between?
Yeah.
Well, let me answer it. Let me answer both questions. The simplest thing is I can write a Spark. I can take those two blobs of RDF that I downloaded. They're somewhat unrelated, and they're not going to link. I would do another presentation where I would actually download data that really does link together to show how it can be put together.
Yeah, so that would be very interesting.
Right. Or I can see if I can write something, or at least I can show you how it's done. But I can write Sparkle queries that would actually connect the data from the two graphs. But if I had two data sets that use the same URIs to identify things, I can write Sparkle queries that would connect those two.
Right, that's because otherwise it doesn't make sense that you distinct disparate things and just put them together.
So it was just keeping it simple, just sort of obtaining the data, but it'd be nice to do another presentation. If there's time, I'm happy to play around and show some more Sparkle queries. We can actually probably do some Sparkle queries against DBpedia. For those of you who don't know, everyone knows what Wikipedia is by now. A European group, I think, wrote extractors and took all the structured data out of Wikipedia, and they created DBpedia. They basically turned Wikipedia into a lot of triples. So if I told you to go to Wikipedia and find a list of all the people, you'd be reading articles for the rest of your life trying to pick out all the people. But you can go to DBpedia and basically say select everything that's of type person, and then pull out all the people, and basically query it as a sort of a totality of data.
How many people are there?
I haven't checked, but I probably should answer my own question. So anyway, the next query I wanted to show is something where rather than sort of grabbing all the data and dumping it, my query is this. I'm basically selecting every subject and I want to get the title and date for those articles. So basically, in the where clause, I'm saying, give me all subjects that have a predicate of title. And this is the full URI of what they use to represent title in these pages. And then in this case, rather than writing a question mark O for just a generic object, I'm putting question mark title. I could use O, that's fine. It's just this is more human readable this way. I use a semicolon to indicate a property object list. And so I put a semicolon, and now I'm basically going to ask for that same subject, I want the date for it, and then bind it to this variable date. So for every time it matches this pattern, I'm getting, in the select list, I'm getting the original subject of what I'm looking for, and then followed by its title and date. And I'm going to run that through the same kind of code here. I'm going to create the query out of it, and then I'm going to iterate through. But now, in this case, I'm going to be a little cleaner about it, is that I'm using this query solution method, and I'm picking off the subject, and then finally picking off the title, and then finally grabbing the date here. And so I'm going to stop the whole thing here and continue this through. Now, this was the my genes I was looking for originally, so I don't know why it didn't show up in the search this time, but it showed up earlier for me today. I basically get this article called My Genes, a Searchable Interspecies Database, blah, blah, blah. And then finally, the year it was published, December 2005. If I had wrote a crawler that started searching for URI after URI for publications, I could basically crawl and build my own database of things. Now that we've got multiple things that have common data properties, I might say, well, give me a list of all the titles. I may look at URIs that represent authors and say, give me all the papers for a particular author. This would be a much more interesting search. And we can try and do that later off of DBpedia. I'll show you how you can go there. So even without doing this, if you just want to just play around and start writing Sparkle queries, DBpedia is a nice place to go to start playing around. Now the next query uses what's called Sparkle Update. In my mind, I tend to lump it together with Sparkle, but there is a distinction between Sparkle and Sparkle Update. Some systems do kind of treat them as two separate languages, and they technically are, but they look an awful lot alike. Apache Genus sort of recognizes that it uses a slightly different library for doing it. In this case, I'm doing an update request. So the update query that I'm going to do is a completely useless query. Sorry, Michael. But just to sort of show you a type of query that actually allows you to manipulate the data. So in this case, in the where clause, I'm matching every triple in the system because everything will be a subject, predicate, object. But I'm going to replace the predicate with this sort of dummy predicate that lumps it all together. So this will basically, for every triple in the system, it's going to create a triple with the same subject and object, but it's going to just give it this lump predicate. And it's going to insert that data and then dump it out. And what you'll see is all the same data that we've seen so far, but you're going to see a lot of these dummy triples in the system. So if you look down here, you can see here, there's, for this particular URI that's of a schema intangible, fantasy fiction, and then lump. So everything is sort of duplicated because of that particular command. That kind of command could be usable in a different case, that I might want to do an ontological alignment between two systems. I might want to map the predicates from one system onto another. So I can write a Sparkle query that will pull off a related predicate in one particular RDF graph, manipulate it, and actually create its equivalent to match it to another system. So with a little bit of Sparkle updates, I can manipulate and match the predicates between the two systems. That would be a bit more useful. The last piece here is now I want to show TDB. What we've been manipulating to date now are in-memory triple stores, which is the Genome model. An RDF term that was introduced is called an Rdf Data Set. An Rdf Data Set is a collection of RDF triple graphs grouped by name graphs. So it's basically a collection of name graphs. But there's also one unnamed graph called the default graph. So you get the one sort of no-name graph, and then every other graph, name graph that's in that RDF data set is a name graph with a specific URI. So to instantiate a TDB database with Jenna is really simple. This one command here, dataset, and then dataset with a lowercase dataset, so those are actually two different things because Java's case sensitive. I now basically create this TDB factory dataset, and I give it the path here. So this / basically is telling it I want it on the root of the drive that this program is in a folder called TDB. So let me find that folder so I can show you what it looks like. So I'm going to delete all of this. So if now I run, and then what I'm going to do is it's going to create a blank TDB database. I'm now going to tell it I want to write to it. And I'm going to add that Genome model as a named graph. I'm going to put it as this URI, ebremer.com/original. And then I'm going to stop it here. Well, let's see if it worked. So there, recreate all the files. So these are all the files. You're not going to directly interact with them, but these represent all the actual data, the indices that make up that TDB graph. And in this particular case, we're going to go one more, I'm going to step down to here. And it's now basically put that data in there, and it basically pulls out that particular, it pulls that graph back out. So it says get named model, and then it basically assigns it to model. So this was the data that I just put in. I'm now pulling it out and sticking it in this variable called org. And then I'm going to basically display the number of triples that got loaded in there. In this case, there's now 344 triples, which is roughly double what we had because I did all the dummy predicate insertions. The last thing that I think I have in the demo here is I'm now going to query this. Now the nice thing about Jenna is the model is a triple store. The data set is a quad store. You have a memory mapped version of both, but then you have the disk-based version of both. The interfaces are practically identical. So if you know how to use Genome model and Genome data set in the memory, guess what? You know how to use it on the disk. And you can basically set up a triple store in 2 lines of code. Bare bones, but it works. And TDB is actually not too bad on a good machine. You get quite a bit of, I've heard as high as 1 billion triples in it. I haven't pushed it to its limit. I've had tens of millions, but I haven't tried to push it to its limits. So in this case now, we're going to do another Sparkle query, a select query, and it's going to be a little different. What I want to do is I want to get a list of all the named graphs in this quad store. So the where clause changes a little bit. I now have this keyword called graph, and I'm specifying G, which is going to bind to that fourth component of the quad, and then the SPO that you're used to seeing. So graph G SPO is going to match everything in that data set, with the exception of, I believe, the unnamed graph. That's treated separately. There's a way to include that, but there's really no set rules on how that unnamed graph works. I've used it for different things myself, but there's not a set rule, so it's a little easier just to use name graphs. And the only thing I want to display is basically the name graph, but I'm going to use the keyword distinct. So what I want to see with this is a list of all distinct name graphs in the system.
So this G will not be mapped bound to null if
that pattern won't match the unnamed graph. It matches everything else. If there's something there. If there are no other named graphs in the system, you'll get back nothing. So I'm going to use the execution factory, but instead of giving it a Jena model, in this case, we're giving it the variable for the Jena TDB quad store, the Rdf quad set, and then basically execute the select. I'm going to iterate through. I'm going to pick off the G's and just display that. So now if I continue that through, it displays one name graph in the system, which is what's expected. Now, I want to show a couple of variations here to make a point. Turn off this. I'm going to rerun the entire program over again from start to finish really quick. There's still only 344 triples in the system, and there's still only one name graph. Question is, why didn't it double the amount of data in the system? And this is there's two important concepts you need to know. For every unique subject predicate, every subject predicate object is considered unique. You can't have a duplicate triple in the same RDF graph. However, when you're talking quads, it's sort of the same thing. But now that you have quads, you can have you can have the same subject predicate object, but it exists in two named graphs, and they're considered different because they're on two different named graphs. So if I keep trying to put the same triples into the same named graph, it will not duplicate those triples because they're considered the same. If I go back here, I'm going to add a 2 on this. So now I'm going to rerun the program, but I'm going to add this data to a new name graph called original 2. And the question is, oh, that was the retrieval, sorry. Put it in the wrong spot. Got to put it here. Rerun it. So now it's listed two name graphs in the system, original and original 2. And what I could have done was I could have added the Harry Potter graph that I downloaded and then the graph on my genes. I could have loaded them into two separate name graphs. I could have called one WorldCat, and I could have called the other name graph and said it belonged to Crossref. What are the rules for it? That's for you to decide how you want to organize your data. But it makes it fairly easy to sort of keep different Rdf data sets separate, but you're also free to merge them. The issue being is if you don't have common predicates or data modeling between them, it's going to be very hard to do Sparkle queries just because you're trying to compare apples to oranges. But if I have RDF that follows the same ontologies or namespaces, I can grab data from 10 different servers, throw it in together, and I can query it as a whole because they all use the same RDF sort of ontology model. You had asked a question before, which I kind of not stumbled on, but I heard it 2 ways. You said, can I query across those two different sources? So the answer is yes, when I've got it loaded local. And I'm not going to go into detail here, but Sparkle has a thing called a federated query. So out there you have what's called a Sparkle endpoint. For many people who are using it, basically it looks like a little web page where you can type a Sparkle query. But a Sparkle endpoint allows you to use it as a protocol and actually do queries against that via a program. And in a federated query, I can actually list 3, 4, 5 different Sparkle endpoints. That query will be pushed out to all 5 Sparkle endpoints, and the data will be brought back and aggregated as a final set of results.
Same query or different queries?
Same query.
Can you send different queries?
You could send different queries. Well, you can send it in the sense that if you write a program, you can execute that Sparkle query against one endpoint and then send another one to the other endpoint.
The same Sparkle statement.
Yes, because with the updates, update queries you could send multiples because you can terminate each Sparkle update query with a semicolon, and each of those could actually be executed against different ones. I don't think you can do it with just straight Sparkle, like a Sparkle select. That's done singular. But via a program, I could easily launch the query and bounce them off different Sparkle endpoints, bringing the data down, and then aggregate them in my local triple store, whether I do it in memory or on disk.
Does Jena support federated Sparkle queries?
Yes, it does. We actually did it when I was working with the Vivo people. Vivo is a faculty profile database for researchers and such, which doesn't sound like it's anything new. But what made them distinctly different was they built it on top of RDF technology, and there's quite a few people use it. Pardon?
In general, you have to write a Java program to federate, actually, right? Because in general, each Sparkle query will go to a separate endpoint.
If you're doing a single federated query, the one Sparkle query will launch it against all of them. If you want each query to be a little different from the others, now you're launching them different.
So the same class, the query execution factory, would run a federated query?
Yes.
Well, that depends on the way you would construct your query, actually, right? Having the privileges go into multiple.
Right. So this is DBpedia. If you can just browse, I think they have a sort of a visual browser on there, but if I go there, I use Sparkle. Oops, sorry. Shot me over to the wiki. So there. So DBpedia runs on top of Virtuoso. There's at least a dozen triple stores out there that I can name. Virtuoso is one of the original ones. It's a commercial product that's open source by a company called OpenLink Software. 99.9% of the functionality is free. You can download it and do whatever you want. The remaining part is what they make their money on, which is usually their high-end clustered versions and such, that and technical support. So here, I can basically type in a query in this box. So I'll type a simple one. I'm going to limit the results. So I'm just going to say grab back 10 triples. So those are the first 10 triples that it finds. So here's some subjects here, and then I can basically look those up, add them as part of the query. So let's take a look at death date. That looks interesting, a little morbid. Well, I really have to be careful what I say. I have to own up to it. I got to find out what the predicate is for it. So if I want to find out, okay, this is giving me a little bit more information about death dates. I wonder how they use this. The question is, are they using it as a predicate or are they using it as a subject? So let's try it as a object. I can see it being a type. Nope. I'll just try it as a predicate now. Kind of weird that they're using it just as a subject. Okay, they're using it as a predicate. So this is basically allowing me to look up death dates for people. So we'll take a look at this person here. Let's see if we can find out. See, some of the difficulties you got to kind of play around exploring the data is find out what kind of predicates people are using in the system so you know how to write your queries. Oops, sorry. I think that there's web pages that they have, I think, that will list a lot of this stuff. So in this case, I'm going to say select. And I want to get this person here. Let's see if we get them in there. Good. I need to put it in brackets. So what I'm trying to ask the system, I'll limit it to 20 for now, is I'm basically saying for the subject rows czar, give me all their predicate objects that they have, well, at least the first 20. Here we go. They use fourth person. Okay. So I can come here. I'm going to take fourth person. It actually looks like they support multiple ontologies. That they'll say this person's a person in like 3 or 4 different ontologies. So what we're going to do is now take say count. Oops. So this should be the query. So let's find out what happens. All right. So I want to say distinct. So hopefully this will answer the question that you got paid. So what I'm going to do here is I'm basically saying find every resource or subject that is of type person, give me the distinct ones and then count them up. And then finally, let me just bind it to a variable. Hopefully it doesn't time out. There you go. So the answer is 1,840,597 people in DBpedia. Better than reading all the articles. Wow, it's actually a lot of people.
Can you search how many of them have a death date? Or the ones that do not have a death date that are still alive? Not exist.
They don't have a death date?
Yes, that means that they are still alive.
Challenging to see how good I can do this off the top of my head. That's fine. So the first thing I want to do is first give me a list of the people.
You say half the people who ever lived are still alive.
But these are famous people, they're in Wikipedia.
All right. So this first phrase gives me all the people, but now he wants the people that don't exist. Now the problem is, what would have been easier is if you said are dead, because then I could have just said this, and I'll explain why it won't work. Death date. Depends. If both person defines, does it define a person, real or fake? Depends on the definition and how they use in the system. If it's supposed to be real, then that'll get the real people. But it would be interesting to check to see if there are any fake people that are under that, because then they've changed the definition to include fictitious people.
These are dead people, right?
Yes.
Well, the question is if for someone who's alive, do they just not list the death date, or do they put a death date with null in there, like, or do they list it with some weird high value? But let's just say they only list death date if the person's dead. Well, this query won't answer the question because this, in the Sparkle where clause, all of these triple patterns are ANDed together. So we can't ask the question. So what we want is a little different. So we want to put a filter on there, and we want to say not to exist, yes. I got this right. Hopefully I think that'll work. And parentheses. And we got to count them up.
If it's a wrong place, you have to switch parentheses.
Count. Distinct S. Yeah, actually, I got to put it out here, but then I have that phrase in there. Yeah, that's right. Okay. All right, let's see if it works.
And I think you need a dot.
Why?
The person, you need dot.
Not before the filters.
No.
Well, let's just say not for Virtuoso. Some systems allow a degree of error in the syntax. Technically, I would need to do this. This would be incorrect. I would have to put this with a parentheses around it. I didn't realize that was legit until I started using Cray has a one of their supercomputers is nothing more than a triple RDF quad store, and I was getting errors, and they say, well, the convention says you have to put the parentheses. They're basically religious to the spec, which is kind of annoying. So if you miss it, you're technically supposed to do it, but every other triple store doesn't require it.
You're missing one from the brace to close where.
Yeah, you are right. I have to close off the whole phrase. There you go. Let's see if it works. Looks about the same. That doesn't seem right.
1,300,000.
No, 1.8, right?
It was 1.8.
Oh, so it's quite a bit alive.
5,000 are dead, and 1,300,000 are still alive.
So now if we change this around, actually,
Or actually, their death date is not known.
so I'm going to take this, I'm going to drop it in here. I'm going to just change the query to the opposite. So we're going to take this out, pull that out, put the semicolon, and so this should count up the number of people that are dead. Seems about right. Okay. Challenge accepted. And anyone else want to throw a curveball at me? I've never done Sparkle off the top of my head like that. Okay. Better for you?
Yeah. I mean, if you have some data sources that can be actually linked, so it will be really like linked data.
Well, I'd actually like to do a talk with a bit more sophisticated stuff. We're gathering quite a few data sources up in BMI. And we're doing some work with Cray to load. One of the projects we do at BMI, actually it's one of the main things that we do. We do a lot of work with what's called whole slide imaging. Take a tissue sample about the size of your fingernail and scan it at a resolution that gives you a picture that's literally 100,000 pixels by 100,000 pixels. That one image would bury a normal computer. And what we try to do in there is that you can zoom in on the image. There's so much resolution, you can zoom in on that image down to the individual nuclei. And the challenge for us is to write software that will actually basically draw a polygon around the perimeter of each nuclei. And then once we have that shape, we calculate about 23 variables: roundness, curviness, oblongness. And we start looking at huge populations of these nuclei. We look at those parameters in relationship to other nuclei around them. For a pathologist to do this, it's not going to happen because you've got about 300 to 500 million nuclei on one of these whole slide images. And we're working with a database of about 33,000 of these. So we have a GPU cluster that does nothing but tries to find all these polygons. Well, the challenge project with Cray is the entire data set's been converted to Rdf triples. It's about 73 billion triples for what we have, and that's only a small fraction of maybe 1/10 of the data, because Cray is happy to see what they can do with it. So they were actually able to choke down the 73 billion triples, which is a pretty interesting feat. And we've actually run some queries in 10 seconds flat. So it's a pretty nice machine they just got. It's got some sick amount of like 100 terabytes of RAM and thousands of cores. So it's a nice little hot rod for me to play with. So, but we're going to have some other data sets that we want to do some federated queries with to sort of get some ideas of performance.
The thing is to send it to the Federated Query and join information.
And I'd like to do a demo and show some of the more advanced stuff they can do with Sparkle. The stuff that I'm doing tonight is fairly simple stuff, but there are some Sparkle queries that can get very lengthy. You also have Sparkle commands where you can actually sort of, instead of explicitly specifying each link pattern that you're trying to do, you can actually just say, find 5 connections away, and it'll start doing more arbitrary type connections. But the data we're looking at is very simple and doesn't really command that kind of detail. But there are data sets out there that have a lot of relationships in them. Like molecular databases, protein pathway databases will have that kind of detail in them. Any questions? Okay. All the source code that we looked at is, like I said, is linked off the site. Feel free to play around with it. Any questions, feel free to contact me. Thank you for coming.
Could you show the query where you were choosing subject, validated object?
Oh, just a simple vanilla query?
Yeah, simple one.
Oh, sure.
You were doing an experiment yourself.
Okay.
What happens to people with an unknown death date?
I mean, this. I'd just be careful running it because DBpedia, well, a lot of the triple stores, since they provide this sort of web interface, it's kind of easy to bury that server writing really complex queries. Virtuoso, I know, is keyed to timeout after a certain period of time. It's to basically protect against people who write a bad query who don't mean to do harm, and then it's also to stop people who are trying to intentionally take down that Sparkle endpoint by overloading it. So I will usually write this with a limit on there, just to see if I can get some data back. going to be hanging around for a while if anyone wants to chit-chat.
I guess in the information below is sort of three endpoints, right? Because they can all be taken down, so
Well,
really use them.
there's some complaints about the stability of these Sparkle endpoints, but a lot of them are very sort of research-oriented, and they're not really maintained as production-grade. DBpedia is probably one of the best. There's a diagram out there for the people who've never seen it. It's kind of interesting. Linked data cloud.
Presumably Google is using it, but it also limits how much information you can get.
This diagram is a whole mess of RDF servers that are out there. It was started, I think, like 2007-ish, thereabouts. And it started off as a dozen servers providing RDF data that were interlinked between the different servers. And this website will actually show year over year how it grows. And so
What does it mean interlinked? You can
You
delete the queries.
this data source has a URI reference to one over here, and this one has a reference over here. It's actually webbed across these different resources. And DBpedia has been there sort of since the beginning, and it's been sort of a major hub for this. Freebase is very much like DBpedia, but whereas DBpedia is derived from Wikipedia, Freebase was sort of a community system built from the ground up on pure data. Freebase was purchased by Google and has basically been consumed into a project called Wikidata. Wikidata is the back end for Wikipedia. So I'm not quite sure how DBpedia will evolve since Wikipedia is around, but all the data that's in Wikidata is actually available as RDF dumps. I'm not sure if they support content negotiation or not. And then GeoNames is a fairly large database of geographical features and so forth. There's a lot of publication data over here. Most of this data over here was created by the Bio to RDF group, which took a lot of traditionally separate bioinformatics databases, and they basically RDFized them, which was kind of cool because there was someone who was asking how to do a particular sort of gene query search. And somebody wrote a textbook, traditional 2-page method on how to do it and connect to these different databases and do the query. And someone who was RDF savvy said you could just go to the Bio to RDF website and type this simple query, because all the work that was in there was bringing these different data sets together to finally execute the query. And the Bio to RDF group was already providing an interface where you could basically have that data together and you could just concentrate on doing your queries. There's a lot of government data, multimedia data. And this whole thing, there's this project? It's a particular program. I actually hadn't heard of it before, but it's some kind of social networking platform. And it provides a lot of its backend data. It's called StatusNet. So it's some kind of social networking software, but they provide all the data as RDF, and so they qualified to be on this website. So it added quite a bit of data to this. And this doesn't represent all the RDF that's out there. There's more RDF that isn't part of this. Most of this data is found at Data Hub, I believe is what they use. But I know I'm working with the Protein Data Bank, and they have 115 billion triples that are available that aren't on this particular graph. Has anyone heard of Schema.org? Schema.org was created by an unholy alliance between Google, Yahoo, and Bing. They got together and agreed on a series of control vocabularies. It consumed quite a few vocabularies that were out there, but they agreed that anyone who marks up their web pages with these data elements would see performance improvements on the search engines. And they were joined by the Russian search engine Yandex, also supports it. Schema.org is basically RDFA and JSON LD. It's RDF. WorldCat actually uses Schema.org for its predicates in its database, which is actually new, because the first time I looked at WorldCat, they weren't doing that. But now they look like they've moved everything over to Schema.org. And if you go to Schema.org.
So I was wondering, still, in what sense DBpedia is linked to Freebase, because they all use different predicate names, completely different.
They don't all. Some of them are actually.
Like this two, for example.
Well, the person one that I just did, this is using this xmls.com/fof. That's the FOF ontology. It's a simple ontology that basically talks about people, their first name, last name, who they're friends with. It's kind of like a little mini sort of Facebook ontology.
I see, so you can link it with the FOF. Okay.
So many of them are using FOF. There's a project done. People are providing a web page about themselves, not via HTML, but basically a blob of RDF data. I've got one that I can show you about me. So this is off my website. So this is basically all the RDF data that I'm willing to share with people. First name, last name, my status is happy, I'm near this airport. But someone basically, as a project, started off with one of these and started following the links, because I actually know two people in here. A colleague of mine, also know Henry Story, who does a lot of work with RDF and social networking. And basically, they followed these links around and they collected a couple billion triples in about a month for all the different FOF pages that are out there. And I think there's actually a site that aggregates them all. So it's sort of like a decentralized Facebook of sorts, as geeky as it is.
Yeah, so okay, so in that sense you can go to the Wikipedia, I guess, and then go to FOF and see, find old friends or somewhere.
But right, when they don't share the same predicates, the data doesn't link, and now you got to do some kind of alignment between them.
For example, they share a person, probably, right? So that's a shared person.
Right. Or in the case of DBpedia, they're actually using multiples. Any other questions? Okay. Have a good night, everyone, and I'll be hanging around.